Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It is our pleasure to have Kai-Wei Chang here from UIUC, and he's going to tell us about practical learning algorithms.
Why they are laughing?
The impractical.
Yeah, we're happy to talk about the impractical.
Okay.
Your microphone on, by the way?
Oh, yeah, it's here. Right, so thanks for the introduction. So a machine learning technique has been widely used in many applications. Right, so in natural language processing, in data mining, in computer vision, people use a lot of machine learning. However, often when you want to train an accurate model, you need to have a lot of data, and you want to design expressive features, and also consider the complex structure embedded in the problems, and often this causes some scalability problems. Right, so to make machine learning practical, we want to have efficient and effective algorithms. So I think the scalability problem of machine learning comes from two directions. One is the data is too big. Another is the structure embedded in the problem is too complicated. So if the data is too big, then even training a simple linear classifier could be a problem. So for example, if you look at like the splice size data set, to load the data, you need 600 gigabyte memory. So if you don't have enough memory, then you will get the trouble. And only another one that if the data, if the structure embedded in the problem is too complicated, and often you have the complexity of your inference and learning algorithm will be increased, and then you also got a problem. So let me show you some example. So this example shows you that making a joint prediction and consider the complex structure of the problem is important. Right, so although you cannot read this Chinese, you know this sign should not mean sleep and fall down carefully. Right? It should mean be careful, don't slip and fall down. But if you look at the local prediction, it's pretty right. So this word means carefully, and this word means slip and fall down. But when these two things combine together, you got wrong. So here is a more concrete example showing why global prediction is important. So imagine in this task, we want to identify the entity type of the noun phrase in the sentence and also recognize the relationship between them. So assume we have a local classifier that can make individual predictions and along with the confidence value. So the blue one shows the prediction with the highest confidence value. And you can see that this local prediction makes some obvious mistake. For example, the second argument of this Boeing relation should not be a person, should be a location. Right? So by considering that we have more confidence on this Boeing prediction rather than in this person prediction, we can use this information to fix our prediction. And then we can get the correct prediction here. And similarly, we can also fix our prediction here. So overall, if you consider the global assignment rather than consider individual assignment, you can get around 2 to the 5% improvement in this data, on this data set.
So just to go, so here you have a bunch of entities. Each entity, you're trying to guess whether it's a person or a location?
Yes. Yeah, we have more tech, but it's just an illustration.
Oh, okay. Yeah. Oh, you have more types, I see.
Yeah.
And then you would normally have a relationship between E1 and E3 too, possibly? Or
yeah, possibly. And also there is an irrelevant relation. So if they are irrelevant, you are just pretty irrelevant. Yeah. Right. So, however, I mean, if you make global prediction, you can get a more accurate model. However, if you consider all the combination of this individual prediction, then the output space can be exponentially large. And this causes some scalability problem. Okay, so the high-level view of my research is trying to design practical machine learning method for big and complex data. And ideally, the method should have the following property that is theoretical motivated, it is efficient and effective in practice, and it has many applications. And the application currently I'm looking at is NLP applications, because NLP problem usually deal with big and complex data in nature. And most of my work are inspired from the observation that learning is often consists of many small components. For example, when
NLP is natural language processing.
oh yeah, natural language processing. Thanks. Right. So usually when you make global prediction, the prediction is based on several local predictions, and also when you want to train a model, usually the training process involves a lot of small updates. So that if we can define some method that we can select and catch those informative components during the learning, then usually you can reuse some computations or simplify the problem, and this can make the learning more easier and also reduce the training time. So my current research contribution can be put into the span defined by these two directions. So in one direction is the size of the data. So a measurement of this is what amount of memory you need to load the data. And another direction is the complexity of the problem, and the measurement of this is what amount of time you need to do the inference. So I start from looking at simple problem, but with some medium size of data. So I study some optimization method, optimization method, the coding design method for a bunch of linear classifier, such as linear SVM or logistic regression. And at the end, we implement our method in a library called LabLinear, and this library has been widely used. And then I start to looking at the problem that the size of data is too big to fit into a memory. So then we need to find some better way to deal with the data. And at the end, I propose a method called selective block minimization method, such that we only need to load the data into a memory once, and then we can get a model as accurate as you loop training on the data. And when I do a PhD, I also working on the structured learning model. So I study how to speed up the training of the structured prediction model in general. And I also looking at the specific case that the structure is too complex, so we don't have a tractable inference algorithm. And I will talk about the work here in this talk. And I also working on trying to learn the latent representation of a knowledge database. So in knowledge database, we recode the relation between entity in a tensor or in a three-dimensional matrix. And then we can able to use a tensor factorization method so that we can learn the embedding of an entity as a factor and the embedding of a relation as a metric. So this is a work I done with Scott E. and Chris Meek during my internship in the Microsoft Redmond. Okay, so as I said, in this talk, we'll be focused on the structured learning. So I will going to talk about some background of a structured learning and then show some general strategy to speed up the structured learning model, and then show you some specific modeling for a specific case that is an online clustering problem. Okay. So in structured prediction task, we want to make joint prediction on a set of output variable and trying to consider the joint loss. So usually those interdependency can be modeled as a structure. So for example, in the POS taking task, the input is a sentence and the output is the linear chain. And in coreference resolution, the input is like a paragraph and the output has a clustering structure. Right? And in dependency parsing, the input is also a sentence and the output has a tree structure. And in segmentation task, the input is like a picture and the output is a set of a binary variable representing the segmentation. So roughly speaking, in structured prediction task, we want to make joint prediction to minimize the joint loss. So in another word, we are trying to learn a scope function. And the scope function can be parametric materialized by a weight factor W and can be defined as a linear scoring function so that we can use this scoring function to assign the highest score to the better structure. Here, the structure, I mean the output assignment. Right, so you can define a feature that based on both the input and the output.
So in this example, so you're trying to figure out what's a noun and a verb and all this, and then you have a score based on how many of those words you get right?
Yes.
Or is it a score based on like whether the whole thing is right, or how did you score?
So in this case, we have a local feature. So the local feature, all this that square is that a feature. Right, so if you get this right, then you get some feature and you get some weight for this feature. And the total score will be the summation of all these weight times the features. Yeah. So it's just like a binary case.
It's not that some mistakes are considered worse than others, or you get extra points for getting the whole thing right, or anything like that.
Oh, here we are talking about how to score the structure rather than how to define the laws. Right, so we in another place we will define the laws. Right, so as you say that in this POS taking test, we have a sentence, we have a part of speech taking assignment, and we want to design a feature based on both of them. And well, if you know H&M, this is like the transition probability, this is like emission probability. Right, so for each this square, you can define a feature.
I'm sorry, I think I'm asking Adam's question again, but so are those weighted equally? I mean, if I find the consonant versus finding the noun, they're given equal weight in the scoring?
No, it's not weight equally because you have a weight factor here. Okay. So you weight based on this weight factor. Okay. Right. So it's like in a binary classification case, you have a weight for each feature. Right. Okay.
So those W's are something that you're given as part of...
You need to learn based on the annotated data. Right. Okay. Right, so in the training, you're trying to learn this weight factor. And in the inference, assume you have the weight factor, you're just trying to predict the best scoring structure. Right, and usually we can define some constraint to reduce the size of the output space. But nevertheless, the output space is usually exponentially large. And for some specific structure, that linear chain structure, you have an efficient learning algorithm, inference algorithm, like Viterbi algorithm. Or like tree structure, you have a CKY. But for the general structure, you can convert this into a integer linear programming problem and solve this by an ILP solver. So I will talk about that later. Okay, so the learning is basically trying to find the W that can give the better performance here. So to estimate the weight factor, if you use an online learning algorithm, this is the thing you want to do, that would, at each time you receive one training data, and then you use your current model to predict on this data. And then you compare your prediction with the gold annotation and use this information to update your model. Right, so if you write down this as a math, and this is a thing you can look at, and this is similar to perception algorithm. The main difference is that in this first step, you need to do inference. And solving this inference is usually expensive. So then the bottleneck of the training will be solving the inference here. And you can also use a batch learning algorithm to train the model.
So the XIs are the sentences, the YIs are the labels of the parts of speech for each word in the sentence. And when you say inference, you're saying it's computationally tricky to, even if someone gives you the parameters, to find the most likely assignment of parts of speech to each word in a sentence.
Just to be clear, like when you say Y is
structure
has an exponentially large, you don't mean that it's of length exponentially large. You mean just basically even if it had even if you had just two possible labels for each word, you will already be exponential. That's what you mean?
Yeah, I mean because you need to consider all the combination of the individual assignment, right?
So if you had like n words, and each one of them could be either a verb or a noun, you already will have like 2 to the n possibilities.
Yeah, exactly. Right.
But they're not linearly separable because the prediction tool makes it so that there's not likely to be multiple verbs in the sentence. Is that the idea? So you have to consider all the permutations, basically, or?
Well, ideally, is you want to consider all the permutation, and you're trying to learn the weight factor such that you can distinguish the good structure from the bad structure. Right. Okay, so if you use a batch learning algorithm to learn the model, then, for example, you can use structured SVM. So this is similar to the SVM for the binary, but this is in the structured case. So in this case, the constraint is basically saying that for all the sample and all the feasible structure, you want the score assigned to the goal structure is better than the score assigned to any other structure by some loss functions. And if this is not satisfied, then you will introduce some select variable and add this into the objective function. Right, so the objective function basically has a two term. This is a regularization term, and this is a penalty term. And C is a parameter to balance these two terms. So it's basically like the SVM. And there is already a bunch of optimization methods proposed to solve this optimization problem. And all of them require to solve many inference problems during the learning. Okay? Mm-hmm.
So there's a scoring function,
right?
Given a sentence and a bunch of parts of speech, and that's some arbitrary function.
Yeah.
Okay. Yeah. And that's why it's hard to figure this out, because you have to consider all possible assignments of parts of speech for figure out the best one. Here you don't deal with that. You just say, well, if somebody gives me, you're ignoring the computation here, and you're just defining what the ideal would be. That the true labels, you have true labels, are better than any other possible.
Yes. So you can consider that the constraint here is there's an exponentially number of constraints here, right? Because here is for all the sample and all the feasible structure. So you have an exponentially number of constraints.
What are the constraints like?
I mean the constraint of this optimization problem for each.
Such that I see. Oh, so.
Yeah, so that's why people propose using a cutting plane method. Yeah, so the idea is basically you want to use an inference problem to select those constraints that is more relevant to your learning. So that you can reduce the search space.
So constraint is a comparison between the correct labels and some possibly incorrect labels.
Okay, so the theory is basically you're saying I need a separation oracle, and the separation oracle needs to solve the inference problem.
Separation, sorry? Oracle? Or?
Because you have exponentially many constraints, so you try to solve this, you need a separation oracle, and the separation oracle requires to solve the inference problem.
Exactly. Yes.
Because you want to find the best the
assignment. Yeah. Okay. Yeah. Okay. So this is a background, and I'm going to talk about a strategy that can speed up the training process. So as we see that no matter you use an online learning algorithm or batch learning algorithm, you need to solve a lot of inference. But existing methods usually treat this separating oracle as a black box. But if you look at the inference problem we are solved during the training, you will find that most of the time, the inference problem has the same solution. So this makes sense because if you consider the possible assignment part of speech tag assignment assigned to a sentence with 5 words, there are no many possible assignments. Although the structure, although the search space is exponentially large. And also another reason is that because we are going to train on the same data several rounds, and the model converges quickly at the first few rounds. So when you see a sample that we have dealt with before, you easily to give them the same solution. Right? So that is many inference problems will share the same solution. And this work is trying to exploit this redundancy by catching the old inference problem so that we can save the
change though, right?
Yeah,
you're doing this during learning. So if you remember an old solution, but your parameters change, then...
Yes, but your parameter change, but you are getting converged, right? So parameter will only change a little bit. And if the solution is not very sensitive to the parameter change, then you are getting the same solution. That's what I mean.
And then how do you? Okay, maybe you'll come to this.
Yeah, that's the main part of the.
So you're going to verify that this is the case.
Right, sure. Right, so here is a key result. Basically, we can use much less inference code to obtain an exact model. So the rows, so this figure shows the number of inference code along with iteration in the training. So the row method basically call the inference solver every time. So this is a straight line. And this is a number of the distinct inference solutions you will observe during the training. So there is a huge gap between these two. All right, so we propose two versions of our method. So this method will give you the exact solution, exact model, and you can reduce around 20% of the inference code. And this can reduce around 90% of the inference code, but you get an approximate solution. But the bottom line is that if you look at the
what is this? What are the bottommost line?
Sorry?
What is this oracle line? Like the bottommost line?
This one? This one? Oh, the oracle means the distinct number of the inference solution you observe in the training.
So I think this is, if I understand this correctly, you're cycling through the data, updating your parameters, and your oracle is just sort of telling you, do you have a different labeling when you come to the same sentence?
I see, but you couldn't predict it in advance, so you needed to do more work. So that's why, like the pink or whatever, the other lines are higher than the oracle.
You rerun, you rerun, you change your parameters, you rerun your learning algorithm, you get the
but
same.
This is in retrospect, you will discover that it was the same one. So,
but you still, even if you know it's the same one, that doesn't tell you. You can still. That's in hindsight.
That's in hindsight. So that's called oracle.
You don't actually. You can't verify that. In order to say that this is the correct one, still requires a lot of work.
Right.
It's a nice hint.
This is why the other lines are above the oracle line. Right?
Yeah, of course. Oracle is that in the hindsight, so you can.
So are you going to tell us what this approx algorithm is doing in a moment, or?
Yeah, in a moment. Yeah.
Absolutely.
I was just going to say, I don't know if it's worth wasting your time or not, but I just have no. I'm an economist and I'm relatively technical among the non-technical people here, and I'm completely lost as to what's going on. I don't know if other less technical people.
What you mean by inferences?
Oh, the inference here, I mean to make predictions on the training data. So in the training data, you get the data and you use your current model to make a prediction. It's basically you assign the value to the output variables.
And you're saying that even doing that takes a lot of computation.
Yeah, that one takes a lot.
And so you're trying to. The goal is to reduce the number of times you need to do that, or increase the efficiency of doing each of those inferences?
I want to do the first one. I want to reduce the number of times I need to call the inference solver.
And the inference solver, what is that like? Could that take any form? Could it be an SVM, lots of different algorithms, or is it restricted to some class of predictors? Or
well, it's like you can think about it like a black box. So whenever I give you a model, I give you this problem, and it gives me the solution.
I see. So the loss function has this parametric structure that you put up,
right.
But the inference protocol could be nonlinear. It could be a tree. It could be anything.
Yeah, it can be anything. Yeah.
And in your example, the inference was, given the parameters of your model in a sentence, what are the parts of speech of each word in a sentence?
Yeah. So my example here is the inference that Viterbi learning algorithm, inference algorithm. So trying to assign the label for a sequence. Yeah.
So just roughly speaking, when you run your thing, because you save about 90% of the code, you run 10 times as fast?
Oh no, it's twice times as fast. Because you also need to spend time on updating the model and also to verify.
Okay.
Yeah. I will show you soon. Right, so basically, this amortized inference framework has two components. So first, we need to have a general framework to represent the inference problem. And then we want to have the condition to check if the two inference problem has the same solution or not. Right, so if you have these two, basically when a new inference problem comes in, you can just go into your cache to look at if there is an old inference problem has the same solution as the new one, and if you can verify that, you just return the old solution. Otherwise, you can call your best solver to solve the problem. Right. So the trick here is solving a problem is usually expensive, but verify the condition is simple. So then you can save a lot of time here.
Does it have to be exactly the same, or is there some notion that things sort of hash to something
What do you mean by exactly the same?
You're checking whether it has exactly the same.
Oh yeah, I will talk about that very soon. Right. So now I'm going to talk about what is the inference framework I use and what is a condition. So we use integer linear programming as a general representation for the inference problem. So basically, you have a binary variable y as to represent each local prediction. And then you can have a linear constraint to describe the interdependency between these output variables. Right? So then you have a scope for each individual little components,
So
and you sum them up.
Now you're opening the black box.
Right, I'm opening the black box, yes.
The inference.
Right, so this framework has been widely used in many NLP and vision tasks, including like dependency parsing or sentence compressions. So basically, theory says that you can represent any maximum probability estimation problem with any probabilistic model using this ILP framework. So this is a very general framework. So, well, a side note here is that although we require to represent the inference problem as this ILP problem, but you don't need to solve the problem using an ILP solver, right? In fact, we only need to use this framework to verify the two problem has the same solution or not, but you can solve the problem by whatever you want. Whatever method you want. Okay, so by this way, we have a way to represent our inference problem. And now I'm talking about how to design the condition to verify if the two problems has the same solution. So basically, we need to have a two condition. The first condition requires these two inference problem has the same constraint and same number of variables. So this is easy to satisfy because when you change your weight parameter, you only change the coefficients of the ILP problem, and the constraints are remain. So for example, if you look at the entity relation test I talked before, the number of equivalent class is only 15. And in each equivalent class, the ILP problem has the same constraint.
What is same number mentions? What does it mean?
Where? Oh, the same number of noun phrase in the sentence in my entity relation example. Well, forget about that. So basically, it's just an example showing that usually we only have a small set of equivalent class, and in each equivalent class, the ILP problem has the same set of constraints. That's just an example.
So two sentences with say the same number of words are equivalent. Is that like?
It's that same number of local prediction you need to take is equivalent.
I mean, this holds trivially for the noun phrase, for the part of speech example, because the sentence didn't change how many words it has, so the number of variables you have is the same somehow.
Right. And also the constraint doesn't change because the constraint only describes the interdependency. Right, so it's okay. Right, and the second condition is that we want to check if the solution is sensitive to the change of the coefficients. All right, so, well, I don't have time to give details here, but basically you can use this condition to check if the solution will change because of change of coefficient. So once you have this condition, then you can apply our model. So you can just replace the black box by these things, and you can immediately see that we can reduce around 20% of the inference code during the training. And as you said, we can actually introduce some approximation by relaxing this constraint. So we can relax this constraint by allowing the epsilon tolerance. And this will give you some approximate solution with some approximate ratio. And if you use a dual coordinate descent method to train the structured SVM, then you can plug in this approximate inference into the learning framework. And then you can prove that the algorithm will stop. And when it stops, the empirical risk is bounded. And also, you can, using the property of a dual coordinate descent method, so that when you use the adaptive epsilon, then you can get an exact model. Okay, so
when you say it improves things by 20%, the number of inference calls, what data are we using to assess this?
I'm talking about the entity relation data set.
Okay, it's a particular data set.
Yeah, it's a particular data set. Right.
Is it Wikipedia or something, or what is it?
No, it's a entity relation recognition test. I talk in the.
So when you relax this constraint in number 2, is that really so you're catching more things now, right?
Yeah, you are catching more things.
That's why you have the empirical risk.
Right. Yeah, so you lose something in the accuracy here. Okay, so this is the end result we have. So you can get the exact model using the adaptive epsilon, and it only requires around 25% of the inference code. Yes?
Sorry, what's in place to evaluate the empirical? Is there a move where you're evaluating the empirical risk so that you have some sense of how loosening that is affecting the accuracy of your data?
Oh, I mean, you define the loss.
So you get to define.
So the empirical loss is static. I mean, the loss in the training data.
What's that definition based on?
So people usually use the Hamilton loss, and you can.
So in the part of
That's right.
So in the part of speech one, is it just the number of parts of speech that you got wrong? So
right.
You said this was a noun, this was a verb, this was whatever you count.
So you're checking against an existing data set.
Yeah. So somebody hand labeled it as the ground truth.
Oh,
correct? Is that right?
Okay.
Yes.
And then you see.
So in all cases, you're going to have some
annotation.
Yes.
Oh. That's why you are asking.
Thank you.
Cool. Okay, so the good thing is, where I am. Okay, so if you use approximate.
So not saving on those, you're just saving on the computation that happens after.
Got it.
Yeah.
We're not paying attention to the computational.
Well, I don't know if the
load
crowd.
of
Do you think the
people.
crowd could label things as nouns and verbs and stuff?
Yeah.
Yeah, sure. Yeah.
That's pretty common. That's a common class.
Is that?
Yeah.
Yeah, so this part is just that improve the computation. Yeah. So this is show you that the training time can also reduce because of you save a lot of number of inference code. So this is the first part of the talk.
So what was the, so you looked at the drop in performance and it was about the same?
Oh, so for these three, they are exact models, so performance
I see.
is actually the same. And this one, the performance is a little bit different.
Okay, so it's a little higher.
Yeah,
a
but
little worse.
it's
Oh, very
okay.
small.
Yeah. Right, so the second part of this talk is how to design a specific model for the problem with a complex structure.
Just go back to that for 1 second. So that
Okay.
whole that can you put that square on there again? Those two numbers. Yeah. So that shows that your algorithm, the approximation, didn't change your performance much.
Yeah.
Right.
Yeah. Yes.
What is this well F1?
What do those mean? Yeah. Can you explain those numbers? What F1?
Oh. Well, yeah.
Yeah. No,
This
just,
is
I
a-
just wonder like why is the first one number smaller and the second number is bigger like that?
Well, it's
The approximate thing is better or is it?
It's empirical data, so everything can happen.
So it happened that the approximate thing was better than the exact.
Yeah, it's possible.
So epsilon here is the same one that controls the relaxation of the constraint, right?
Right. So
How do you adapt epsilon?
oh, so this adapt epsilon is that you use a large epsilon at the beginning, and you're trying to reduce the epsilon
And you do this
gradually, and at the end you use 0, so you just solve the exact things.
But you change it manually. There's some
Yeah, we change manually. Yeah, with some tuning. Okay, yeah, so let me go to the second part. So motivation of this part is doing a coreference resolution problem. So in coreference resolution, give you a paragraph, you want to identify all the noun phrases that represent the same entity in the real world. So for example, in this paragraph, Bill Clinton, president of the USA, and he are referenced to the same guy, so you put them in the same cluster. Okay, so we can model this problem as a supervised clustering problem. So assuming we have a lot of this kind of paragraph with a gold annotation, and we want to learn how to do this clustering. So this is different from the unsupervised clustering task that people usually have the similarity metric. But here we also want to learn the similarity metric along with learning the clustering.
But some other algorithm or some other person came along and broke it down into the entities. You're not looking at the problem.
Oh, yeah. We assume we have an entity given. Yeah. Right. So the task is basically to learn how to define a clustering function from the training data. Right. So as I say that we can define the similarity metric between the mentions and then use this similarity metric to learn the scoring for the cluster. And then we can parameterize this similarity metric by the weight factor with the feature. So the feature can taken from like the string similarity or position of the mention in the paragraph.
So just to understand this, presumably he is supposed to be equally similar to Bill Clinton and Vladimir Putin. So
right. So that is a hard problem.
So how do you decide that he belongs to Clinton and not to Putin?
Right. So we have a feature like the position in the paragraph, so you know they are close to each other than the Putin, and also in other cases you know the gender of this guy. So if this is a woman, this is a man, then you know he should be linked to this one. And also you have another feature to describe the things.
Okay, but the similarity function, so its input is not just the name Bill Clinton, it's also like the position inside the paragraph.
It's a
On the next slide, it didn't seem to show that, right? So here you simplified it because you said, the similarity between those references, it actually involves a lot of other features.
Oh yeah, I didn't put it. It is also including the context, not just these two words.
In principle, if one had a large corpus, one could design features based on side information.
Yes.
Like if New York City and the Big Apple were frequently co-mentioned in other parts of the corpus,
yes,
then in the context of the present sentence, even if they are not near each other in the sentence, you might learn that they have a high similarity. So
right.
Does your method incorporate that somewhere?
We kind of have the feature have this kind of information. So we have a feature from a system called NESIM. So NESIM is a system to measure the entity similarity by just do the random word in some graph as knowledge graph. So in that case, I guess it might cover some kind of feature you mentioned, but maybe not all.
Okay. So that's a similarity matrix that someone else previously produced by training a machine learning algorithm, and now it becomes a feature in your algorithm?
Right.
Thanks.
Yeah, but I mean, here we talk about like modeling, so you can use any feature you like. Okay, so the goal here is that we want to learn a clustering scope based on this similarity metric, and so that we can do the prediction of a clustering. So one straightforward way to design the clustering scope is just use all the within cluster pair, and then you just sum up all the similarity between them. So for example, in this case, if you get clustering like this, then the cluster scope is just the sum of all the red edge and this blue edge. But if you do this, then the inference problem of this is basically a correlation or clustering problem. So people know that this is NP hard and it is intractable. So in the literature, because we cannot do this, so people just using some heuristic. So what they did is that they decouple the learning of a similarity metric from doing the clustering. So they basically use a binary classification method to learn the similarity metric, and then use a greedy algorithm to do the clustering.
So this problem that you mentioned is, I mean, it seems very similar to max cut or right. I mean, if you only had two types of edges, whereas two things are either similar or dissimilar, then in some sense it's like max to lean or so it's it's a problem that has like an efficient approximation algorithm.
Yeah, maybe the thing I'm going to say is similar to what you suggest. Right. So I mean, to do the binary classification, basically people get the positive data from all the within edges in the gold clustering, and get the negative data from the across edges from the gold clustering. So then you can use that to train a similarity metric, right? And then you can do the greedy clustering in the inference time like this. So basically, you just go from left to right, and in the inference time, when you sit on some mention, you look at all the mention in your left-hand side, and then trying to find the one with the highest score. And then if the score is larger than some threshold, then you put this mention into the same cluster as in this mention. Otherwise, you create a new cluster. Okay? So if you do this, then basically this creates a left linking forest such that all the mentions in the same tree are in the same cluster. Okay? So, but as you can see, there is an obvious drawback of this heuristic, because when you do the learning, it is decoupled from when you do the inference. So the goal here is that can we learn a better similarity metric such that we can do better when you do the inference. So that's why we propose a best left linking latent model such that we can jointly learn the similarity metric with the clustering. So the idea is we define a latent structure as this left linking forest. As this left linking forest, so that we score the cluster by using the edge in the forest rather than all the within cluster pair. And because this is a tree structure, so inference and learning in this structure is easy. So then you can use this to jointly learn the similarity metric and clustering. Okay, so here is a live demo. You can go to this web page. So give a paragraph. We can generate a latent left linking forest to represent the coreference cluster. And the good thing here is this tree structure not only gives you the cluster, but also gives you some reasoning of why we generate this cluster. So for example, you can see that those mentioned has more information are usually in the middle of this tree structure, and that pronounce is usually in the leaf of this structure because they have less information. And you can also see that these two guys are linked together because they share some string in their representation. Okay. Okay, so the remaining question is how we learn these things. So recall that we have an annotation as a clustering structure. But now we want to use a tree structure to represent the clustering. So if we want, to learn this model, we need to define the latent forest as a latent structure. So what I mean is that when there is a new data come in, you are going to use your current model to predict on the sample such that you can generate a latent structure that is consistent with the gold clustering structure. And then you can use this and your predict structure to do the update. And mathematically, you can write this down as a latent structure perception algorithm. And also you can use other latent structure model to learn these kind of things. Okay, so another extension of this is that I say that now we use the best left linking structure to score the clustering. So a natural question is that can we use a distribution of all the left linking forests rather than you just use the best one? And the answer is, of course, yes. Right? So you can basically score the probability of the clustering by all the left linking forests that are consistent with this clustering. And the score of the forest is summation of all the edges in the forest. And after you have a definition of this probability, you can just use the regularized maximum likelihood estimator to learn the weight factor. So it's like the standard way people learn a probability model. Okay, so for the empirical result, you can see that if you just do a local learning, you get suboptimal performance. And if you use this best left linking tree, you can get a jump in performance here. And if you consider a distribution of a latent left linking forest rather than just one forest, you can also get some improvement. And comparing to other model, when the paper is published, our method is outperformed than other models. And this guy is also using a similar latent structure as us. So we both get a good performance here. Okay, so I also done some other work along with these structural predictions. So from algorithm perspective, I also proposed another parallel learning algorithm for solving structural SVM. And from the modeling perspective, I also looking at semi-supervised learning for the.
If you go to the view slide, so.
Which one?
So so the one we right before.
This one?
Yes. So you improve things. You're saying basically from 61% to 63%.
Right.
And since then, like what's?
Oh, you mean? Yeah. So this problem has been studied like 15 years. So people already propose a lot of different kind of method to deal with this. And although most of them are heuristic, but they also get good performance. And recently, in 2012, the NLP guys decided they want to have a shared task so that people can compare with all the methods. So this is a data that from that shared task.
And right now you're like right now your result is the best that's known for this task?
Not for now, but it's for this around 2013. And now people also propose other methods, but the interesting thing is the following words are all use this latent kind of tree structure to run the model. Yeah, but they kind of using different feature and consider different phenomena in linguistics.
So they use your what approach. Are the numbers that they're getting just?
I guess so people, they also change the estimation, they also change the performance metrics, so it's changed a little bit. Our method get around like 60 in the new performance metric, and the state of the art is like 61. Yeah. There is, I mean, NLP is like the Kai so. Right, so as I said, I also do some modeling work that this is done with Kissy when I was was the intern of him. We do the semi-supervised learning for structural prediction problem with complex structure. And also I work on the search-based structural prediction model in this summer with General Inference and Hao Dao-Mei. So if you are interested, I can talk about that offline. Yeah, so most of my things are applied in NLP tasks. So I also study other NLP tasks and also release a package and software demo. Right, so this slide is an overview of all the research I have done so far. And in the future, I want to also work on this direction to design practical machine learning tool and method for large and complex data. So from the machine learning perspective, I want to design a method such that I can deal with big and large data and can support several applications. And from the application perspective, I want to study the application and use that to inspire the design of the algorithm. Right, so there are a few projects I'm working on now and also in the near future that are search-based prediction. So these two are like machine learning projects are trying to design the new method for general latent structure model or search-based structure prediction. And these two is that the application-wise study that we're trying to apply our method to relation extractions and also on course document coreference. So this is a correction problem that not only consider the entity in the same document, but consider the entity closer documents. Okay, so this is all the people I have collaborated with. I guess you can recognize some of them. Right? They are from Microsoft. And in conclusion, basically, I think the key scalability problem in machine learning are because of the data is too big or too complicated. And I already studied several ideas to deal with this scalability issue that I can do selecting, caching, or parallel descent to reduce the training time. And I talk about 2 different work that I have done during my PhD, and I hope I can do more in the future. And all the code and demo can be found in my webpage. Yeah, thank you.
I wanted to understand, thank you for your talk. It was very helpful and clear. As a non-technical person, I understood almost half of it.
Oh, that's cool.
It's a total compliment. No, I think I got more than that. I want to understand if you can apply this to segmentation problems or dependency problems, what that would look like, or why those are maybe not part of your problem set.
Oh, so I mean, I'm proposed the general framework for dealing with different kind of problem. So whenever you have a problem that you want to make joint prediction of kind of interdependent variables, you can apply this method.
Do you see any challenges to applying this approach to those other issues of segmentation, or to? I mean, do you see anything that wouldn't?
You mean like that segmentation example of the bird in the background? Image segmentation. Mm-hmm. Did anyone apply this to image segmentation, or could you apply it to image segmentation?
I think no. I mean, we can apply for that. I mean, people in the computer vision literature, they use the structure model to deal with that task. Yeah. So I think they even have the implementation. You can just download. Right.
So, this is just more a question about these kind of constraint set methods. You're sort of implicitly assuming these problems aren't noisy, in that there's sort of one right answer for each sentence, and if there's really one right answer, then yeah, these constraints sort of work. But if it's actually noisy, you kind of really have to consider multiple explanations, and then one, like, do we think there are real possible bumps in performance? Like maybe it was ambiguous what the person who put in that sentence was, not to the algorithm, but as a person. Then somehow the algorithm really needs to consider multiple explanations. Do you have an idea how to deal with those issues? If I didn't care about computation, I'd just say, sure, I'd be Bayesian and I'd do inference and I'd consider all explanations, but that's not a very satisfying.
Right. So I think there are certain cases that you just use the individual assignment should be good enough if the problem is not ambiguous. Right. But yeah, in our case, we usually consider the cases that you need to make global prediction so that you can get accurate model. But
by over prediction, meaning that actually means you're trying to deal with this by considering multiple other possible explanations.
Yeah.
I see.
Right. And well, of course, you can study other perspective of the problem that using a human effort to.
Yeah, but that does seem to help. So you do actually consider multiple possible explanations when you're training these things.
Do the humans tend to agree? Or
so I think the latent structure thing is more like what you say. So, right, you have a latent structure. Basically, each latent tree is one explanation of the clustering. And then you consider the distribution, and you consider all the explanation. Yeah, but for the first part, the general structure prediction framework, I think people usually assume you only have one best assignment, and didn't consider different kind of explanation or different output.
Right, but I mean, maybe offline, but it's not just that you have one best assignment. It's that there's noise in your training data set is always going to have one best assignment.
Right.
But the issue is if two things is sort of it's a coin flip.
So I think one thing maybe I can add on is that you can define your loss, such that you can treat with the loss function so that you can actually model those noisy or multiple explanation there. Right? I'm not sure how to do that actually.
Do you do that in the ESL cases? So when you said there were applications, to Sean's question,
Right,
it seems
so
like if you're working with material, let's say poorly written, so the parts of speech example is a good one. Your examples are a well-organized paragraph. But if I'm working with someone who's written a poorly organized paragraph, then it seems like this application would be really challenging unless you're looking for patterns of organization that are connected to other language problems or language issues, like another and somebody who's is that what the
well, this is not the
is?
thing I'm doing, but it's exactly happen when we deal with that data set. So in that data set is they give you the ESL writing, and you want to correct the grammar of this writer, right? And we find that if you get a very poor written text, then all the part of speech text, all the things are very bad. So at the end, we actually just using the surface string as a feature to do the things. Right, so that's an interesting research direction to trying to do what you suggest.
Questions? Thanks again.